Okay guys, so today we're going to be working on how to solve kinematics problems. Kinematics is the umbrella term for any motion problem. There are typically three main kinematic equations that we talk about. And these three kinematic equations all come from the two basic equations, which is the velocity equals change in position, or the displacement, over time, and that acceleration is change in velocity over time. Okay? If you go on YouTube, you can find the derivations of the equations, but they all stem from those. So let's talk about the equations. Here are the three main equations, and it's important to know when to use them. So if we look at the first one, okay, we have v, okay, so velocity, equals initial velocity plus acceleration times time. Okay, this one we use when we don't have and we don't care about distance. Okay, we can use it to solve for final velocity or initial velocity or acceleration times time, but it is when we are not given and we don't want to find distance. Where this has x, typically this equation is rewritten as delta x equals v initial times time plus 1/2 acceleration times time squared. Again, that's just by subtracting this over here so that it becomes x minus x naught, which again can be rewritten as delta x. Okay, so notice in this equation there is no final velocity. We use it when we don't have and we don't care about the final velocity. Typically, this is used in basic distance problems if something starts from rest or anything like that. And last but not least, we have v squared equals v initial squared times 2a x minus x initial, which remember we can rewrite as delta x. Okay, this one, notice it doesn't have time. It's for when we don't know and or we don't care about time. Okay, so those are the three kinematic equations. We typically refer to them as equation 1, equation 2, equation 3. Okay, different teachers might have different numbers for them, but these are three of the basic ones. So let's do some problems and see how we use these. An apple falls from a tree. Okay, step 1, I'm always going to draw a picture. Okay, so I'm going to draw my picture. There's my apple. Kind of looks like a heart, but okay, that is my apple. Okay. And it falls. If it fell from a branch that was 3.4 meters high, okay, so the distance that it fell is 3.4 meters. How long will it take to hit the ground? Okay, so we're looking for time. Time is our unknown. That is what we are trying to find. And looking at this, you might think we don't have that much information, but we actually have a lot more information than it seems like. For example, if something falls, okay, like an apple falling from a tree or you dropping something from your hand, what speed does it start out at? Okay, well, initially it's not moving. So your initial velocity is 0. Okay, we also know something else. Why is it going to fall? Well, it's going to fall because of gravity. So we know its acceleration is negative 9.8 meters per second squared. Okay, this is always the acceleration when something is falling, or when something is thrown up in the air, or when something is launched horizontally in the air. It is pretty much always the acceleration for things that are in the air. Okay, and this 3.4, that is our change in position, which since it's vertical, we're going to use y instead of x. So delta y, 1, it's falling down. So delta y is going to be negative 3.4 meters. Okay, so that's all we have. We know we want to know time. We know our initial velocity. We know our acceleration. And we know our change in position. So let's look at our equations. Okay, I thought I had the equations right here. Apparently not. Okay, let's go back and look at them. If we look at our equations, okay, The one that has distance, initial velocity, acceleration, and time, it's going to be our second equation. Okay? So, if we look at that second equation, it is change in this case we're going to do y because it's vertical, equals v initial times time plus 1/2 acceleration times time squared. Okay? So, our next step, see if any of these things are 0. Okay? If you look at this, v initial is 0. 0 times time, it doesn't matter what time is. 0 times anything is 0. So we can just ignore this part of the equation and pretend like it doesn't matter. Because it's 0. It doesn't matter. And then, next step, plug and chug. So we plug in the numbers that we know. First, delta y is negative 3.4 equals 1/2 times our acceleration, negative 9.8, times time, which we don't know, squared. Okay, there it is. Okay, 1/2, 1/2, aka 0.5, times 9.8 negative equals negative 4.9. Okay, so negative 3.4 equals negative 4.9 times t squared. To get the t squared by itself, divide by 4.9, divide by negative 4.9. That cancels out. So we have 3.4 negative divided by 4.9 negative equals 0.69. Okay, so 0.693, we'll just leave it at 0.69. So 0.69 equals t squared. To get the actual answer, we got to take the square root of it. There's the square root button. Square root of it is 0.83. So 0.83 equals time. And you never want to forget to add back in your units. So 0.83 seconds equals time. Okay, time is in seconds. That makes sense. The apple does not take very long from when it falls to hit the ground. 3.4 is not very high, so that totally makes sense. That's my answer. Let's look at another problem. A car is speeding down a road. Okay, so we always want to draw a picture. Okay, there's my car. It is speeding down a road when a dog runs out in front of it. The car's brakes can cause a deceleration of negative 8.7. Okay, so it's going to be stopping. So if this is its initial velocity, its acceleration is going to be in the opposite direction. Okay, so acceleration equals negative 8.7 meters per second squared. If the car comes to a stop 5.6 seconds after hitting its brakes, okay, so first it's going to be going and it's going to be stopping. So its final velocity, okay, the final is going to be 0. That's what speed it ends up at because, you know, it's stopping. Okay, and that happens in 5.6 seconds. So time is 5.6 seconds. How fast was the car going and how far did it go before it came to a stop? Okay, so let's talk about how fast the car was going first. That is our initial velocity. So we need an equation that has initial velocity, acceleration, and time, and final velocity, because that's the information that we're given. So we're going to be using this equation right here. Okay, can move those out of the way now. Maybe, or not. Okay, so the equation that we're using is V equals V initial plus acceleration times time. Okay, so let's go ahead and solve it. we have our V initial, V final is 0. We don't know our V initial, that's what we're looking for, plus acceleration, which is negative 8.7 meters per second squared, times time. Okay, we need to get the time by itself, so first we're going to move that V0 over to the negative side. That makes it become negative. So negative initial velocity equals negative 8.7 meters per second squared times time. Oopsie, we had our time. Always remember to enter in everything that you know. 5.6 seconds times 5.6 seconds. Okay, we can't do a problem if we have two unknowns. Okay, so the negative and the negatives can cancel each other out. Okay, and we're left with 8.7 times 5.6. 8.7 times 5.6. Dang it. 0.7 times which gives us 48.7. So our initial velocity is 48.7. Second squared cancels out with seconds, so it's meters per second, and also because it's a velocity. Okay, so now we know that our V naught is 48.7 meters per second, and we can add that to things that we know. The next part of the question says, how far did it go? Okay, so distance is typically represented by delta x. Okay, so let's go ahead and move this part of the problem. Okay, I'm gonna move it off to the side now that I have that written over there, and let's look back at our equations. So now we need one that has delta x. It can have the initial, it can have the final, it can have acceleration, it can have time. We could use either this equation or this equation. Both of them are going to give us the same answer, but because this one has the x already on the side by itself, I'm going to go ahead and use that one. Okay. So, again, typically we rewrite that equation by moving the x over. So it's delta x equals v initial times time plus 1/2 acceleration times time squared. And then we plug and chug. Delta x equals our initial velocity, which remember we found it's not 0. It's the number that we were given. 48.7 meters per second times our time, which was 5.6 seconds. Move it all over. Okay. Plus 1/2 times our acceleration, negative 8.7, times our time squared, 5 points. Dang it, running out of room. .6 squared. Okay, and then we got to plug that into the calculator. 48.7 times 5.6. 272.7. The seconds and seconds cancel out, so it's meters. 272.7 meters plus 1/2 times negative 8.7 times 5.6 squared. Okay, so it's easier to do 5.6 squared times 8, dang it, 5.6 squared times 8.7 negative times 0.5 equals negative 136 plus negative 136. Okay. And you add that up. Okay. So I'm just going to do that number plus 272.7, and you get 136.3, which we can just round and say 136. So the car went 136 meters. A rocket needs to reach a speed, oh, there's a typo there, of 718 meters per second in order to enter orbit around Earth. Okay, so we know that its speed, final speed, has to be 7,800 meters per second. Okay, for a rocket. If the rocket's thrust engines can provide an acceleration, net acceleration, so that just means it's overcoming gravity, of 5.50 meters per second squared, another typo, how long will it take to reach the necessary speed? So time, we don't know. Okay. So, in order to find that, we also need to know, what do you think the rocket's initial velocity is? That's something else that we know. Well, the astronauts everything needs to get in. It's going to start at a speed of 0. Okay. So, we're looking for time. If we look at our equations, it will be quite easy for us to use the first equation. Okay? Say we weren't looking for time. Okay? Say we wanted to go straight to how far it was going. Then we could use the third equation. And I'm going to go ahead and do that part first just to show you guys how it works because we haven't used that equation yet. Okay? So that one is v squared equals v initial squared plus 2 times your acceleration times delta x. Okay. V initial is 0, so we can cancel out that term. So we have v squared, which is 7,800 meters per second squared, equals 2 times our acceleration, 5.50, times delta x, which is what we're trying to find. Okay. So 7,800 meters per second squared is, where'd my calculator go? A big number. It is 6084000. So 60,840,000 equals 2 times 5.5, which gives us 11 times delta x. Okay, so we take that big number, divide it by 11, and we get 553,00909. Okay, so 5,553,000 meters. Okay, that's how high it will go. And that makes sense, okay? It's going to go pretty high because it needs to get outside of Earth, okay? Earth's atmosphere ends at 160,000 meters, so yeah, that would take it pretty high up. Okay? So that is delta x. Very big number there. Normally we aren't working with these big numbers. We would probably change that to kilometers or something more reasonable. Right? Now let's go back to our original thing and say we were solving for time. So if we were solving for time, we could just use this first equation. It has v naught, time, acceleration, and v final. Okay. So again, that equation is v equals v initial plus acceleration times time. Okay. V initial is 0, so we can ignore it. V final is 7,800 meters per second equals our acceleration, 5.50 meters per second squared, times time, divide by 5.50 meters per second squared, divide by 5.50 meters per second squared. Plug it into your calculator, and you get 1 1,418 seconds equals time. Okay? And typically we don't want to leave our units like such a big number. So what we could do is we know that there are 60 seconds in 1 minute. Okay? Seconds and seconds cancel out. When we divide that number by 60, we get an answer of 23.6 minutes, which is much more reasonable a number. It looks better. We can figure what that number is a lot easier. So typically, if you get a really large answer for seconds, you'll want to convert it to minutes. And if it's still really big, convert it to hours. They're all times. It's all fine. Okay, so that's kinematics. Hopefully that was helpful. Did you get it? Okay, cool. Okay, cool.